Hello everybody, this is me again, Yusuf Saleh, chemistry teacher. Because the section 2-3 is too long, that's why we forced it to get it two parts. So today we're going to study the second part of this section, and the first title, the first topic is conversion factors and significant figures. What do we mean by this? We mean how do we deal with the results when we have in calculations conversion factors? Here it's written in bold, in calculations involving conversion factors, the results keep unchanged, which means do not round anything and do not pay attention to significant figures. Why? Because the significant figures are defined, not estimated, not measured. Are defined, not estimated, and not measured. So they will not be rounded. So for example, here we have convert, this example, we have convert amount of, okay, let's move this upward. Okay, now, sorry. This is the given amount. The given amount here is in meters, and the question asks to convert it into what? Into centimeters. So the given in meters, and the solved amount or the unknown is into centimeters. And we know that 1 meter equals 100 centimeters. That's why we're going to have two conversion factors, 100 centimeters per 1 meter or 1 meter per 100 over 100 centimeter. Which one we're going to use? Of course, we're going to use the one that involves the required unit in the numerator. Centimeter here is in the numerator, so that's why this conversion factor. We cannot use a conversion factor 1 meter per 100 centimeter here. Why? Because the required unit here in the denominator, so we need it in the numerator, so this one is not suitable, not appropriate for this calculation. Now, we have a rule says the unknown amount or the amount solved equals given amount, which is this, times conversion factor. So this is the conversion factor, and the given amount is the one given in the question. After calculations, we have the given amount times the conversion factor, 100 centimeter per 1 meter. We get this result that contains how many digits, how many significant figures? 4. Despite we have here, or even here, we have 100. But we will not mention about this. Why? Because this calculation involves multiplication by conversion factor, and these conversion factors are identified, are certain, are not measured, not estimated. So any calculations that involves multiplication or division with conversion factor, the conversion factor is here. So we will not change the result. We will not round the result. Let's move forward. Okay. We have scientific notation. Actually, scientific notation is extremely important. Why? Sometimes we have numbers, these numbers are huge, are too long. So for example, when you say number of atoms in a sample, number of atoms in a sample, you will say, okay, I have in 1 mole, for example, I will say 6.02 and many zeros, about 20 zeros. So you cannot deal with this number every time. You write 6 and you write after it 23 zeros. This is impossible. Instead of this, we're going to convert these big numbers into scientific notation. Scientific notation involves two parts, as we see here. We have M, which is the mantissa. We have M, we call it the mantissa, and we have 10 power to N, the mantissa, and the exponent here, which is 2 base of 10. So here the M is the mantissa represents number less than 10, which means not 10, equals or greater than 1. It is less than 10, which means 9, 9.9, 9.9 is accepted. But 10 is not. You cannot use 10. You cannot use 10. You can use 9.9 or lesser until you get 1. Also 0.9 or 99, this is not accepted. Why? Because it's less than 1. But 1 is okay. 1 is okay. Now, let's be back to the main formula. The main form is mantissa times 10 power to n. Here, and this n actually must be small, but the computer made this mistake. N represents represents the exponent that can be positive or negative. It can be positive or can be negative. And significant figures are these appear in M, which means the significant figures are not the ones in the exponent or what. No, only the ones in the M. For example, the number 6.5 times 10 power to 4. Okay, here is the mantissa, the M. How many significant figures? It has 2. So the whole number has 2 significant figures. And the value of 6.5 times 10 power to 4, which means 65, it means here 65,000. 65, we have one here is wrong. Okay, it is 65,000. How can we decide? We're gonna put the number of places to left of the decimal equal to what? Equal to the exponent here. So here's the decimal 1, 2, 3, 4. 1, 2, 3, 4. Also, sometimes the exponent can be negative, but let's have more positive exponents here. And let's move. Let's have more examples. We have example 2, convert the measurement of these kilograms. Okay. These kilograms. This number is 247,000 kilograms into scientific notation. Okay, we have 2, 4, 7, 0, 0, 0. The point is here. We're going to change this into scientific notation. So we're going to move the decimal 1 place, 2 places, 3 places, 4 places, 5 places. Okay, which means it is 2.47 times 10. Okay, what's the n? What's the exponent? How many places the decimal moved? The places the decimal moved to left, 1, 2, 3, 4, 5. So this is 5. Why positive? Why not negative? Because the decimal moved leftward. And the number is minimized. The number is minimized. As we can see here, it's the same. Example 3, let's see an example that, okay, that will involve negative exponent. Okay, this example it says expressing a small amount such as, okay, this amount is small, which means this is smaller than 1. This is smaller than 1. Sorry, let's remove this. Okay. This is smaller than 1, and we have many zeros. We need to, in this case, we need to get it in scientific notation. Move the decimal point 4 locations. 4 locations. Okay, so this becomes, let's move this 1, 2, 3, 4. Okay, so this after movement equals 1.2 times 10 powered. How many locations, how many places it moved? 1, 2, 3, 4. Rightward. As long as the decimal moves rightward, it would be negative. Let's repeat. 1, 2, 3, 4, rightward. So the scientific notation here for 0.0012 is 1.2 times 10 power negative 4. Okay, now let's move forward. When moving decimal leftward, the exponent equal positive value of the number of places passed. And when the decimal moves rightward, when moving the decimal rightward, the exponent equals negative. So when you go rightward, the exponent is negative. When you move forward, leftward, the exponents are positive, just like in the two examples before. Now we have mathematical operations using scientific notation. So first, addition and subtraction. In addition and subtraction, we must get the exponent equal first. We must get the exponent equal first by moving what? By moving the decimal and get them equal. So here in this calculation, we have addition of two amounts, 2.4 times 10 power to 4 kilograms and 7.9 times 10 power to 3 kilograms. We'll see that we have here is 4 and here is 3. We must get them equal. So we can do this by raising this into 4 or lowering this into 3. So we have two techniques. In the first technique, we have raised the 3 into 4. Okay, when you raise this into 3 into 4, to 4, you raise it, so this must be minimized. So this will, the 7.9 times 10 power to 3, let's move this here. So this becomes what? Becomes 0.79 times 10 power to 4. Despite this is not scientific notation, but this is necessary to achieve the calculation. So we have the exponents will be copied as they are, and we add these 9, 9, and 4. This technique is when raising the lower exponent. Also, we can have lowering the higher exponent, which means the 4 will get 3. When we minimize the 4 into 3, the decimal will not move leftward. It will move rightward. So we have here, earlier we had 7. Sorry, not this one, this one. 4. Let's remove this. We had 4. Sorry. We had 4.2 times 10 power to 4. So we will get the mantissa and the 10 power to 3. So we said we're gonna move the decimal where? Rightward. So this becomes 42 times 10 power to 3. And we can add this with the other amount already has exponent of 3. You see this one we use here. after getting the exponent equal to the other one, as long as the exponents are equal, so we're gonna copy down the exponent and add these two. Later, we must treat this. Why we must treat it? Because this is not scientific notation, because this is greater than 10. So we're going to move the decimal again into between 4 and 9. So we will have 4.99 times 10 power to 4. How would this happen? When moving the decimal. Moving the decimal, this causes increasing the exponent. So moving the decimal leftward increases the exponent by 1 because 1 place. So also this can be rounded into what? Into 5.0 times 10 power to 4. Why this rounding? Why this rounding? Because here we have the number of digits to right of the decimal equals 1, and the previous rules we talked last mini lecture. Okay, now let's move forward and see what we have. We have also multiplication. Okay, multiplication and division with scientific notation. In multiplication and division, we're gonna multiply the first mantissa with second mantissa multiplication. Add times 10 power to the first exponent plus second exponent. So example, we have actually, this is the first mantissa. This is the second mantissa. First exponent and second exponent. So first mantissa times second mantissa, 5.23 times 7.1. Okay. And the powers here must be added. The power 6 plus minus 2, which means minus 2. So this becomes, here we have 37 times 10 power to 4. Of course, 37 is not the mantissa. That's going to move the point here into here and increase the exponent by 1. Why? Because only one location is moved. So it becomes 3.7 times 10 power to 5. How many significant figures here? Two significant figures. And it is fit with the one here because it has 2 significant figures. The result also will have 2 significant figures. Of course, here we have micrometer times micrometer is micrometer square. Okay. Now, what about division? And division, we're going to divide the mantissas, mantissa first, divide by mantissa the second, times, here we have n1 minus n2. n1 minus n2. Okay, here we had addition of them. Addition, but here we're going to have subtraction of the exponent. When multiplication, the exponents are added, the powers are added, and in division, the powers are subtracted, which means we're going to multiply the first mantissa with the second mantissa and 10 power to n1 minus n2. Let's have an example. In this example, we have 5.44 grams times 10 power to 7. 5.44 times 10 power to 7 grams divided by 8.1 times 10 power to 4 mole. Okay. We're going to divide the two mantissas times 10 power to 7 minus 4. So 5.44 divided by 8.1. It becomes 0.6716 times 10 power to 7 minus 4, which is 3. Of course, in the given here, we have only 2 significant figures. That's why we're going to regulate. We're going to adjust the result to have 2 significant figures also. Adjust to 2 significant figures. Of course, we're going to move this, this decimal. We're going to move this decimal here, and we're going to increase this decrease this by 1. So why? Because the decimal is moving rightward. So this is gonna lose 1. So it becomes 6.7 times 10 power 10 square gram per mole. Okay. These were about the scientific notation with addition, subtraction, division, and multiplication. We have here sample problems using sample problems. Sample problems, in order to get your work organized and avoid the mistakes, it's better to have the solution of your problem through 4 steps. The step 1 is analyzing the question, which means read the question carefully and determine the given data and the unknown. So decide the given and the unknown. Don't forget, at least you must read the question twice, 3 times better. Okay, so here we have, in this step, read the question carefully, twice at least, and determine given and the unknown. Second, get your plan, draw your plan. What are the relationships you're going to use in this problem, in this solution? So put the rules in order that you will use them. Sometimes you need some conversions before the main law. So put the conversion laws, relationships. So in this step, make a plan how to use the given data to reach the unknown, decide the laws or mathematical relationships required. Keep in mind, sometimes you will need more than one step, sometimes not one relationship, sometimes maybe 2 relationships, maybe more. After you have drawn your plan, you wrote the rules, the laws, compute, which means make your calculations, which means replace the variables by what? By numbers, the numbers that you get them from the question. Okay, so get the result or the answer. Finally, evaluate your answer. Is your answer logic? Are the units are correct? Are the significant figures are correct also? So an evaluation involve 4 steps, sometimes less. So for example, checking the units are the units are correct. So for example, you're calculating the molar mass. We know that unit of molar mass is gram per mole. I cannot find it a gram per volume, for example. And the volume, for example, is with meter cube, maybe centimeter cube, maybe milliliter, maybe liter. It depends on the given data. Second, estimate the expected answer. You may be earlier, you made an expectation, a prediction about the answer. If you find the answer is very far from your prediction, make a revision to your work. Make a revision to your work. Why? Because sometimes you get some results are not logic, not reasonable. So for example, we know that the gases are light and their densities are, if you find the density of a gas, for example, 2 grams per milliliter, this is not logic because the density of any gas is much less than this value. So you must revise your work. C, check the order of the magnitude. This is the same one that we said, if they are reasonable or not. And the example here about gases is fit to this point. And finally, make sure that the answer involves correct number of significant figures. Check the significant figures. So the significant figures, when multiplication or division, must be equal to the one in the fewest. And so, we have a practice here. This practice actually present in your book, in your textbook. what is the volume in milliliters of a sample of helium has mass? We have the mass. Mass is 1.37 times 10 power negative 3 grams. Given the density of helium is 0.17847 gram per liter. This is a gram per liter. But the question says I need it in milliliters. The question says in milliliter. And the given here gram per liter. Why? That's why we need to convert the density into what? Into gram per milliliter. Okay, so first analyze, which means I'm gonna write down the given information, the mass and the density. We're gonna write them here. And also the unknown. The unknown is samples volume in milliliters. That's why I must treat this. So in step 2, to find the volume, you can use the rule volume equals mass divided by density. But actually the density must be treated first. And we must use conversion factor. The conversion factor, we have 1 milliliter is 10 power negative 3. So we need to multiply by 1 liter divided by what? By 1000 as conversion factor before. Okay, let's move forward. Oh, sorry. Okay, density in grams per milliliter equals density. Of course, the milliliter is much lesser than liter. So that's why we expect the density in gram per milliliter much lesser than 1,000 times less. So we have the given density times the conversion factor 1 liter by milliliter, and this becomes this amount of gram per milliliter. You see this amount is much lesser than the amount given in a gram per liter, because liter is much larger than milliliter. Okay, so we convert it into scientific notation. Scientific notation 1.7847 times 10 power negative 4 gram per milliliter. Now we can apply the rule mass divided by density. It's mass divided by density, and we found it's blah milliliter. Okay, the answer must be rounded to 3 significant figures. Why 3 significant figures? Because we have here the fewest significant figures, only 3 significant figures as given in the text of the question. So that's why we're going to round this into 3 significant figures into here. So this because the 6 is greater than 5, it will be added, which means increasing the 7 into 8. Step 4, we're going to evaluate our answer. The evaluation of our answer, we can see that the units are correct and the volume is expected. Why? Because already we have a mass is low. So that's why it's okay. The magnitude of the answer is okay and expected, and the significant figures are correct, and the unit is correct. So it's okay. Let's move to next title. Next title, we have direct proportionality, and also we have inverse proportionality. Sometimes we hear this directly proportional and inversely proportional. What does it mean, direct proportional and inverse proportional? Direct proportional, we have 2 variables raised together, drop together. And when one of them increases, the second also increases. For example, volume of a gas increases when temperature increases. Of course, when pressure is constant. When we have direct proportionality, we have the product of division is constant. the product of division here must be constant. Okay. When two variables are directly proportional, the product of division must be constant. Also, we can have this y, the variable, first variable or second variable equals the first times k. And we have the proportionality with letter of alpha in Greek alphabetical. So x is directly proportional to y. When drawing the relationship, we will have a straight line. This straight line is correct about the proportionality, directly proportionality between mass and what? And volume. So for example, you have, this is mass and this is volume. And increasing the mass increases the volume also, when other factors or conditions are. So you can see that it's straight line and it passes through 0, 0. It passes through the point of 0, 0. This is all about the direct proportionality, and we have here the inverse proportionality. It's exactly opposite to the stuffs we talk about in direct proportionality. These two variables, when one raises, the second drop. When one raises, the second drop, which means they increase and decrease inversely. And instead of having the product of division equal to constant, here we have the product of multiplication is constant. The product of multiplication is constant. Of course, we can get use from this relationship to find one of the variables. For example, if we need to find y, we're going to say y equals k divided by x. Of course, k is constant, and x is this alpha is directly proportionality with the reverse of y, which means 1 of y. When drawing the graph, we're going to have a line such this, and this is known as hyperbola. Hyperbola, you see, hyperbola, it drops and have a curve, a bend. So we see that when the pressure increases, volume decreases. Pressure increases, volume drops. So volume and the pressure of gas when temperature is constant are inversely proportional. Why? Because when pressure increases, the volume decreases. Let's see. At pressure of 250 kilopascal, 250 kilopascal. What is the volume? Volume is about 200 centimeter cube. Okay, when pressure increases more, and 400 about 50. Let's see what is the value of. It's about 150. You see, pressure increases, volume decreases. So pressure and volume of a gas sample are inversely proportional, because when pressure increases, volume decreases. This is with one condition, if we have the temperature is constant. So the proportionality here is inversely proportionality. When the two variables, one of them increases, the second decreases. And this is all about the section 2, 3. Next lesson, we're gonna have some section reviews and chapter reviews. I wish you get best benefit from our mini lectures, and have a nice day.